How's it going? I'm recording a fresh video here for these last couple of mini videos covering our last learning goals on molecular orbital theory. So I just wanted to freshen things up a little bit. All right, let's get it going. So MO theory is very similar to valence bond theory. So it's largely based in quantum mechanics, and we look at simple molecules, okay? But what's powerful about molecular orbital theory is we're able to expand this into much larger molecules, okay? So let's go through a few definitions here. So MO theory is a bonding theory based on the mixing of atomic orbitals of similar shapes and energies to form molecular orbitals that extend across two or more atoms. Okay, so we're starting simple, right? Two atoms basically is all we'll really look at in this class. Okay, so a molecular orbital, so often we write this as an MO, okay, is a region of characteristic shape and energy where electrons in a molecule are delocalized over two or more atoms in a molecule. So that delocalized, it really means they're like spread out. So let's write that down. So that means like spread out, or even, sharing, right? So we're talking about making a covalent bond here, okay? So a bonding orbital is a region of increased electron density between nuclear centers that serve to hold the atoms together. Okay, so really this is like an extension, right, of this molecular orbital to really specify that we're talking about a bonding orbital. And constructive interference is the key here. And if you recall from our chapter 7, right, when we have constructive interference, okay, when I add two waves together, I get an even brighter spot, okay? So we think of these orbitals as having wave properties. So when we have two atomic orbitals overlapping in this way, okay, they're going to create this constructive interference that we call a bonding orbital, okay? So if we have let's see, regions of increased electron density in a molecule that destabilize the molecule because they decrease the electron density between atoms. That's what we call an antibonding orbital, and that's due to destructive interference. So if now we have these two waves and they are out of phase, so in other words, where we have a peak, we have a trough, and when we have a trough, we have a peak, and so on and so forth, right? So if these things are out of phase like this, then they cancel and we end up with nothing, okay? So even though these orbitals are rather complex ideas, it's rooted in this very simple idea of adding waves together and getting regions of constructive interference that give us bonding or regions of destructive interference that give us antibonding. Okay, so let's keep going with this. So here we have an MO diagram, okay? So we'll write that down, MO diagram, molecular orbital diagram. And we start here by having two separated, in this case, hydrogen atoms. So we're making the H2 molecule here. So we start with two separated hydrogen atoms, and there's an electron in each one of these, okay, as represented by the dot. And I drew it, with our point up, spinning up arrow, okay? And as these get closer to each other, they can create that bonding orbital, okay? So I'll write bonding. Or, depending on the sign of the wave function and the spin of the electron, which gets kind of more into that complicated quantum mechanics details that we're not too worried about, this is our anti-bonding orbital. And we can see that the anti-bonding orbital is much higher in energy than the bonding orbital. So there is a benefit when these two hydrogens get together, the electron spins become paired up, down, and this creates our bonding orbital, okay? And as you can see here on this energy diagram, the way that we draw these things, so here we have our 1s, let's see, that's our 1s, I'll say AO, so that would be an atomic orbital, and those mix constructively, right, to make what we call the sigma 1s bond, okay? And so we've talked about the sigma 1s bond before, the sigma bond in valence bond theory. And just to remind you here, right, I've got my little Mathematica program that I wrote. And I've got my two separated hydrogen atoms, right, as is shown in this picture. And I can bring them closer and closer together. And you can see what's pretty cool here is when I get them to where they're overlapping, there's now constructive interference in what we call the internuclear zone, the internuclear region, right? This space between the two nuclei. And we can see that that constructive interference leads to a bond, okay, which is pretty cool. And so now here going through the equations to make the antibond in my model here. So you can see now when I move these closer together, they end up interfering destructively. So you can see there's no bond that's created between them. And if I get them closer and closer and closer, it's almost like they're repelling each other, right? You can see the way that those two orbitals don't want to mix to form that bonding orbital. So that's the antibond, okay? So continuing along, so again, we kind of talked about sigma bonds and pi bonds before in valence bond theory, but we'll just go through these again because this is really important for MO theory. Okay, so we recognize when I add a 1s and a 1s, I make a sigma, and specifically a sigma 1s bond. And what makes this a sigma bond is that it is cylindrically, oh God, whatever that says, symmetrical about the internuclear axis, okay? So if I were to look down that axis, it would just look like some kind of a, type of a cylinder, right? Where there's one nuclei and there's one nuclei, okay? And so we can see that. I showed you guys that right here, okay? There's our sigma 1s bond. So I can make a sigma bond in another way. And so if you recall now with our p orbitals, right? Our p orbitals look like these lobes. And we can have the px, the py, and the pz. And of course, if we're doing this in order of increasing energy, right? We remember that we first, with our AOs, our atomic orbitals, we start at 1s, okay? Then we can move up to 2s. And then just slightly after that, we've got the 2p. And so that 2p, right, will have px, py, pz, okay? So now when we have the pz orbitals, so we specifically call our internuclear axis, let's draw like a reference line here. We call this axis the z-axis, okay? So if I was drawing a three-dimensional coordinate scheme, perhaps that's y and that's x. We just, as a reference frame, we just call the internuclear region the z-axis, okay? So as a convention. So that's why when we were talking about our two pz orbitals here, notice that they're oriented towards each other, okay? So I've got that in my simulation here. Let's see, let's find it. Somewhere down here. Yes, I think hopefully this is the bonding and not the anti-bonding. Okay, so but you can see now I'm moving these two pz orbitals. Yes, and there we go. So I'll separate them. So there's my my two pz orbitals, right? Each one of these is a 2pz orbital, okay? And as I move them closer together, you can see that they get that beautiful overlap here. And in this image, right, this kind of white region right here, each one of those would be the nuclei. So what's really interesting is here, like one of these nodes, these anti-bonding regions, is predicted to be on the other side of the nuclei, and as well as this respective nuclei. However, all that matters is that they've got shared delocalized electrons between them. So that's what's bonding them together. Okay. So now if I reorient my p orbitals, and so I suppose based on the way that I drew this, we would need to call this one the x and this one the y. Let's fix that. So right, so these are oriented up and down, so perhaps that's x. And these are coming out of the page, so that would be y. So that's a better way to label that. So now you can see we get a different kind of bond when those orbitals are reoriented. And again, I want you to recognize that each one of these are individual atoms, right? So this would be an atomic orbital, and this would be an atomic orbital, right? And we're bringing them close together and we're bonding them. So my Mathematica model here is only a two-dimensional model, so I think that I only have one of these orientations. Yep, let's do it. Okay, so here's my, we'll call these the px orbitals. And so you can see they've not quite interacted yet, maybe just a little bit. You can see they're getting kind of interested in each other. And there we go. When we get them close enough, you can see they're making this lovely overlap constructive interference. Okay. And so this pi bond, right, if you recall from our valence bond theory, this is what makes our double bond. Okay. And then similarly, we could also have, you know, in this model, right, if my orientation is like this, I could rotate it, you know, in and out of the screen, right, which I don't have in this model, but hopefully that makes good sense from this picture. Okay, right, so I'll draw that axis again, right? So there's the y, there is the, oops, nope. That would be the x. Okay, and my z dimension is this internuclear region. Okay, so in fact, my nuclei are really like right here and right here, or here and here. Okay, so that's what makes these different than a sigma bond. The sigma bond has that overlap between the two nuclei. The pi bond has that overlap above the two nuclei. All the same, that can still keep them bonded together. Okay. Alrighty, so now what about our antibonds? Well, as you saw in the simulation for the sigma, right, that they just never create any type of overlap, right? So perhaps here would be my nuclei and here would be my nuclei. So we call this a node, right? Just like we did in atomic orbitals, okay? And so if we go through and look at some of these simulations now, let's see here. I think that I have the pi antibond. Okay, yep, so you can see I got that close together and they never form that overlap, which you can see here, it is right here. So we denote that these are antibonds by putting in this little star. So that little star right there tells us that that's the antibond, okay? And similarly, if I go through some more of these here, so there was my sigma, my sigma 2p bond, but what about my sigma 2p antibond? You know, this one right here, right? So as I move those closer together, you can see that it looks just like the other picture. They never form that overlap, and if anything, they are interfering with each other destructively. That's why you see them kind of going away, right? Okay,